All right, let's get right into the review for the polynomial and nonlinear systems test. So for these first couple problems, there's a couple different ways that we could attack it. So the first one's a fifth degree polynomial with 3 real zeros and 4 turning points. So we need to either have, we got a couple different choices. One is I could have a pair of imaginary zeros, like that. So here we have 1, 2, 3, 4 turning points, and 1, 2, 3 real zeros. I could also use 2 double zeros if I wanted to, but we'll look at one of those later. A second degree polynomial with 3 real zeros and 2 turning points. Well, if it's a second degree polynomial, then it's only going to have 2 roots. That's the max it's allowed to have. So this is not possible. For number 3, a third degree polynomial, whereas as the function goes to the left, f of x goes up, and as the function goes to the right, f of x goes up. Well, this is the pattern for an even function, even degree function. And it asks us to draw a third degree, which is an odd degree. So this is also not possible. A third degree polynomials with factors of x, x plus 2, and I think there's supposed to be an x minus 5. I think that got cut off on the sheet, and exactly 2x intercepts at -2 and +5. The problem is that if x is one of our zeros, the other zero should also be a 0 there at the origin. So this is also not possible. A fifth degree polynomials with 5 turning points and exactly 2 real zeros. Right. Now this one's a little bit like the first one. So start here, there's a turning point. Now what we can do is we can make our turning point and our 0 the same. So now we have 2 zeros. Oh, you know what? You can't do it, because 5 turning points on a fifth degree can't do that, right? Remember, you're always going to have max number of turning points is degree minus 1. So if it's fifth degree, the max number of turning points I'm allowed is 4. So this is also not possible. All right, an odd degree polynomial, a is less than 0, and when we say a, we mean leading coefficient. And a double root at -3. So remember, a double root means that we get something like that. Or we can also do something like this. It's not quite perfect, but you get the idea. So a is less than 0, which means that the leading coefficient is negative. And that means it's going to start down here, and it's going to end up here somehow. So what I'm going to do is I'm going to come through, hit the double 0 there, turn, come back through, and now we've got it. We got an odd degree polynomial. Oh, I did that backwards. Come on, people. Hold on. I apologize. If it's a negative leading coefficient, it's going to go down. So I need to go down to 3, like that. Sorry, did that backwards. All right, even degree polynomial, leading coefficient positive, 2 turning points, 2 real zeros. Easy enough. So I know I'm going to go here. Oh, I'm only allowed 2 turning points and 2 zeros. Well, I don't know if I can do this one. Let's see. Let me think about this for a second. Hold on. Sorry, the announcement.
Mr. Bimber, Ms. Lewis, Ms. Collins, Mr. Thornton, Ms. Joseph, Ms. Gates, and Ms. Clark.
All right. Sorry for the interruption for the announcement. So this one with 2 turning points, to do 2 turning points, that means I'm going to go one direction, turn around and go the other direction. So I'm going to be in opposite directions when I'm done. So I can't do that with an even degree polynomial. So this is not possible. Okay. As x approaches infinity, as we go this way, the function goes down. As x approaches negative infinity, the function goes up. I'm allowed 1 real 0. Huh. Well, this is a trick one. This is easy. You ready? There we go. Straight line, 1, 0. As x approaches infinity, f of x approaches negative infinity. Right. And as x approaches positive infinity, negative infinity, x approaches f of x approaches infinity. So the easiest way to do that is just with a straight line. All right, for this one, I believe we are now on number 12. All right, so as the function goes, as x goes to negative infinity, this part, f of x goes up. So we're going to be like this. And as x goes to infinity, the function goes up. So we'll have something like that. But I'm not allowed to have any real zeros. And that's easy enough. Let's just do a parabola up that never crosses the x-axis. And so that's it for the problems where we're supposed to draw our own graphs or look at the properties of polynomials. So solving a system of equations. We can do it algebraically or we can do it graphically. And for this test coming up, I recommend we do it graphically. You're more likely to get the correct answer. So, to graph the system, just put them both in the calculator. And then we'll go right into the graph. Oh. I don't know what happened there. And there's our graph. And it's kind of hard to see, so let me show you one of the tricks that you can do here. Is if you hit zoom, there's the choice for zoom in. And how you use zoom in is you move the cursor to where you want to zoom in to. So I want to zoom in here where it looks like the intersection is. And sure enough, there are two. Whoa, I'm going to have to zoom back out. I zoomed in a little too tight. I want to center it right about here. So we're going to zoom out. But there's definitely an intersection there. So what I want to do is, I'm going to zoom back in, but I'm going to center it on the origin. So there we go. Now I can see the two different intersections. And so we're going to go to second, calc, intersection. And ask for the first curve, and that's our first part of the system. And as for our second part, there's the second part of the system written up here. And so we then just click guess, and we're just going to go as close as we can to the point of intersection and hit enter. Now, here's where we have to be careful. What number is that? That's really 0, 2. And the reason that we know that that's 0, 2 is because the x values in scientific notation. That's really, and I'll write it over here, is really 0.01. It's that number. So that's really 0. So be careful with that. The other way, and then we got to find the second intersection. Let's clear that. So we clear that, and we go back in. Here we go. Intersecting, first curve, second curve. And now we arrow down to the second intersection, which is occurring at -1, -1. So those are our two intersections. If you really wanted to, you could do this algebraically. You would do 3x plus 2 equals x squared plus 4x plus 2. Subtract 3x from both sides, and subtract 2 from both sides. And we get 0 equals x squared plus x. And we can factor that as x times x plus 1. And by the zero product property, either x equals 0 or x plus 1 equals 0. And we get x equals -1 or x equals 0. And then we would just plug one of these values here back into the equation to get the corresponding y's. You plug in 0 for x. 3 times 0 is 0 plus 2 is 2. And there's your first point. You plug in -1. 3 times -1 is -3 plus 2. And there's your -1 for y there. All right, same thing here. Now, this one's a little trickier because we can still do it using the graphing calculator, but this equation is not solved for y. So in order to solve it for y, what I'm going to do is I'm going to subtract x from both sides, and I'll get -y equals -x plus 1. And then I will divide both sides by -1, and I'll get y equals x minus 1. Mathematically, you can multiply both sides by -1, but that seems to confuse the algebra students. So now I have my two equations that I can put into the calculator to find the point of intersection. And so we'll go back, we'll go to y equals, clear out, and I have y equals x minus 1. And over here, clear that out, and I will have y equals the square root of x plus 1. And when I graph them, I'll zoom standard, and there's the point of intersection, so I will calculate it. What? Let's try again. Left. Wait, I hit the wrong button. Second calc. I want 5 intersection. First curve, second curve, guess, and there's my intersection, 3, 2. So solution is 3, 2. This one's a little bit harder to do algebraically. I can say x minus 1 equals the square root of x plus 1. So I can square both sides, and I'll get x squared minus 2x plus 1 equals x plus 1. You subtract x from both sides, subtract 1 from both sides, and you'll get x minus x squared minus 3x equals 0. And so we'll get two solutions, x minus 3 and x. So either x equals 0 or x equals 3. The problem here is that we squared both sides. And remember, when you square both sides, you have a potential to get an extraneous solution. So we have to check both of them. So if I plug in 0 for x, I get y equals negative 1. But if I plug in 0 for x here, I get y equals positive 1. So this is an extraneous solution. The only solution that works is this one. And y equals x minus 2, so y equals. And so on this problem, it was definitely easier to use the calculator. All right, let's answer some general questions. A polynomial has a function at x equals 2. What must be one of the factors? Well, remember, then the factor has to be x minus 2. Polynomial function has a 0 at x equals negative 6. What must be one of the factors? X plus 6 must be one of the factors. And this is just that relationship. List the apparent factors of the graph. Use f of x notation to describe the end behavior. So here are my zeros. My zeros are at negative 3, 2, and 4. So the apparent factors of the graph are x plus 3, x minus 2, x minus 4. The end behavior is f of x goes to, remember we have two options, either x goes to negative infinity or x goes to infinity. So the question is, what is f of x doing there? And I know this seems backwards. I told you the SOL, they use Yoda speak for whatever reason. They put the determinant before what it determines, but that's okay. So as we go to the left, the function's going down. And as we go to the right, the function's going up. All right. What are the y-intercepts of the function y equals x squared plus x minus 6? Well, you can graph that and look at what the y-intercept is. And I'll show you that real quick. Maybe. Let's just clear out my graphs here. X squared plus x plus 6. And we see the y-intercept is at 1, 2, 3, 4, 5, 6. This is an easy one, though, because, oops, I typed that into the calculator wrong. Sorry. Let's try that again. No. It was minus 6 was the graph that we were trying to do. And we'll see a y-intercept at 1, 2, 3, 4, 5, negative 6. But if you remember, when we had ax squared plus bx plus c, c was the y-intercept. Either way, knowing that fact or by looking at the graph, we shouldn't have any problem getting that answer. All right, write the possible equation for the function with the factors of x plus 3 and x minus 2. Well, that would just be f of x equals x plus 3 times x minus 2. Now on the SOL, though, they may not give it to you in this form, so you may have to FOIL it out.
Elena Douglas, go to room 2114. Elena Douglas, room 2114.
And so we get x squared plus x minus 6. And they may leave it for you in that form, or they might write y equals but you have to be able to recognize that these two would be the equations that have those as their factors. All right. What is the apparent zero of the graph? -3. Remember, zeros are the x-intercepts. List the zeros of the graph. Use f of x notation to describe the end behavior. So, those are the zeros. -3, 2, and 4. This is actually the same graph as number 25, so the end behavior is once again the same. As x goes to -infinity, as we go this way, the function goes down. And as x goes to infinity, f of x goes up. Sorry, this should have been -infinity. I think I miswrote that. All right. Find the zeros of the function x cubed plus 2x squared minus 5x minus 6. Now, when you see this, what they really want you to do is to use the polynomial long division and then factor it all the way out. That's making life a lot harder than it has to be. The easier way to do this problem is to just graph it and look at what the zeros are. Remember, we have the graphing calculator. So, x cubed plus 2x squared minus 5x minus 6. -3, -1, and 2 are the zeros. And sure enough, if one of the factors is x minus 2, then one of the zeros has to be 2. So, g of x only has the factors of x, x plus 1, x plus 3, and x minus 2. What is the solution set for g of x? 0, -1, -3, and 2. Remember, g of 0 is 0, g of -1 is 0, g of -3 is 0, and g of 2 is 0, because if they're a factor, then they are part of the solution set. All right, what are the factors of a polynomial whose graph has the x-intercepts of -5, 0, and 1? X plus 5, x, and x minus 1. And really, the key to this test is understanding the relationship between factors and zeros. If you have any questions, bring them to class, but otherwise, I will see you tomorrow or the next day.